Good evening, all participants, respective participants from different faculty members from various institutions, postgraduate scholars, research scholars for joining the session today. Greetings from Division of Electronics and Communication Engineering, Karunya Institute of Technology and Sciences, Coimbatore. Today is the fourth day of the AICT ATL-sponsored 6-day online FDP program on AI/ML-based reconfigurable antenna design for next-generation wireless communication. So to have the first session, we are having a distinguished academic leader and an inspiring researcher, Dr. Jude Hemant. He is professor and head of ECE Department, Karunya Institute of Technology and Sciences. Jude sir is a renowned researcher with over 2 decades of teaching and research experience. He is an IEEE EMBS distinguished lecturer and has served as a visiting professor at reputed international universities, including the University of Luxembourg, University of Oradea in Romania, and Samara State Medical University in Russia. He is listed among the top 2% of world scientists by Stanford University for the previous 4 years, a testament to his outstanding research contributions. His expertise covers areas such as computational intelligence, biomedical image processing, and decision support systems. He has also authored and edited more than 60 books with leading international publishers such as Springer, Elsewhere, and CRC Press, and has served as an expert reviewer and research evaluator for several international agencies. Sir, we are truly honored to have you this evening. I warmly welcome Jude sir to deliver the session. Dear participants, sir will be delivering the session on the topic AI and ML, core concepts for engineering problem solving. Welcome you, sir.
Thank you, ma'am, for your introduction. Am I audible, ma'am?
Yes, sir. Yes,
okay.
Audible.
Let me share my screen. Is my screen visible?
Yes, sir.
In full screen mode?
Yes.
Are the slides moving?
Yes.
Okay. So thank you, Dr. Shinelet, for the introduction, and thank you, participants, once again. I welcome you warmly for this ATL FDP program, and I hope all the past 4 days would have been much more useful for you, and you are in line with another day to get more information for your research career. The participation is very good, but the only point which I have some concern is the time, and the mode is online mode. I am not very sure how many of you are listening on the other side, right? But I will advise you, each session may not be completely beneficial for you. That is absolutely fine. But there will be some triggers, there will be some takeaways for you in each session, which will be definitely useful for in your research career. So I sincerely hope and request that you be attentive for the rest of the session and the next session also. So the topic given to me is artificial intelligence for problem solving. I am very sure that for the past few days you were hearing more information on the antenna side, and as per the protocol, today we are slightly moving towards artificial intelligence, which is also the integral part of the title of this FDP. However, you can definitely take the concepts of these artificial intelligence, which I'm going to give you, and if you are working in antenna design applications or any other communication related applications, you can definitely put them into practice. And for this session, I am not going to generally talk about AI, but I am going to talk about a pressing issue among research scholars and professors. Every time, whenever you meet any academician or researcher, the first thing they say is we are struggling to get some quality publications, right? Leave alone the funded project consultancy, patents, and all the other things. So why do we struggle in this publication process? The main reason is our process of doing experiment or our process of doing research is not up to the expectation of the research community, be it antenna, be it AI, whatever it may be. Why? The research community always expects us to solve some problems. We need to develop some methodologies, engineering methodologies to be precise, to solve some problems. Most of the time, trust me, 99% of the time, we are giving more importance on developing solutions. Okay? More importance on developing solutions. That is absolutely fine. You may ask, that should be the way. Yes, fine. But the question is, what are you trying to solve? Have you identified the clear cut problem? There we miss a huge hole in the application part. We do not give importance to the problem, but we always say that we take some random problems and make sure that I have developed so and so methodology or so and so algorithms or so and so design, and I have developed a solution. But finally, what happens? Whenever you submit a paper, your article will be rejected. Whenever you submit a proposal, your proposal will be rejected, right? So problem solving is a phrase, right, where the first priority or importance should be given to the problem statement. And for the concrete, complex problem statement, you need to find the solution. Most of the time, our problem statements are very, very weak. They are preliminary, they are very shallow, for which there is no necessity for a solution, to be precise. Okay, so my request or my desire is to identify or to help you identify complex problem statements for different AI related applications. Right? We have studied different AI and ML methodologies. Probably those who are sitting on the other side, you must have also learned about different machine learning methodologies under this broad umbrella of AI. But trust me, they are not framed randomly. There was a problem, right? In the previous framed methodology, they identified that, and to solve that problem, a new technology emerged. But that point or that gap is always a gap even now. We just look at the importance of methodology. But today I am going to give you some case studies or some examples of the existence of a problem and how methodologies were developed to solve that problem. So that when you go back to do some problem solving for your application, you also will think in that angle. Right? So I am going to ask you a question rather than giving an answer. Are problem statements and methodology related? If the problem statement becomes complex, your methodology cannot be a traditional methodology, right? You need innovation, you need invention so that your problem can be solved, that complex problem can be solved with the innovative methodology. Right? So that is the agenda with which we are going to have for the next probably till 7:30, 1 to 1.5 hour session. I will be handling till 7:15 or 7:20. Then we can have a question answer session. If you need, you can unmute your mic and ask, or otherwise you can post it in the chat box. The organizers will help in uh, giving the questions to me. Right? So every researcher should have one PowerPoint slide like this, which will talk about their credentials. Right? It is not to tell to other people, but to motivate themselves. Research is all about motivation. When you lack confidence, when you lack motivation, you will be always under pressure to move forward in your research. Right? Where does this motivation come from? Not from other outside or externally. It should come from inside. To pump up with energy, You have one PowerPoint slide and keep on changing the credentials in terms of numbers and also bullet points. To start with, it will be very less. That is absolutely fine. When you keep on moving further, your credentials will definitely grow, right? These are some of my credentials which I have illustrated here, and these are some of my editorial positions in international journals, right? When I started my experimental works, I made mistakes. I made terrible mistakes. But during the course of time, I changed the way in which an experiment has to be done so that my publication scenario increased exponentially, which paved the way for other credentials. So if you can also do that, you can also enter into such high level positions in journals also. If there is any match, you can always let me know if you need any support, any of these journals. And these are some of the books. Once you get some good experimental work with some publications, you will be automatically invited, or you will be given the opportunity to write or edit books with standard publishers like Elsevier, IEEE, Springer, and so on. Right? That will add more credential for you. These are the base with which a researcher should move forward in their research career. These are just for you to motivate and make sure that you do a clear cut problem solving for your application. Let us come to our agenda. Artificial intelligence is a very broad area. Everybody knows that, right? Under artificial intelligence, we have a subset called as machine learning. We try to train the machine with as much data as possible and make the machine solve a problem. What problem the machine is going to solve? Not a problem which can be solved by human being, but a problem which the human being finds it difficult to solve. That is the reason why we go for machine learning, or that is the reason or objective why the concept of machine learning came into existence. Under machine learning, again, we go one step deep. There are plenty of methodologies available, right? And I have taken some case studies which is close to antenna design applications also. You can try to optimize the power, you can try to optimize the radiation pattern, everything with the help of this ANN and deep learning. You can find plenty of papers, research papers available in this area. So I have taken these topics and we will see one by one what is the problem associated with that and how they solved by developing an innovative methodology. Traditionally speaking, artificial neural networks, 20 years back or 25 years back, people were praising artificial neural networks like anything, right? They are very much useful for all classification, regression, prediction, association, clustering in any application, be it communication engineering, be it civil engineering, mechanical engineering, people were using it heavily. But one single person, okay, a research student under the guidance of Professor Hinton, he had an idea. Why he had an idea? Because he encountered a drawback with artificial neural networks. Right? What drawback he encountered? Before that, we will look at the diagrammatic representation of a traditional neural network and its advanced version, the deep neural network. You see that number of layers and the neurons in the traditional neural network is less. Now, on the other side, you will find that the number of neurons or the layers in this deep neural network is very high. What is the need for increasing the layers? So whenever you are using deep learning or deep neural network, the first question you need to ask is, what is the need? Why can't I stick on with my traditional neural network? What difference am I going to anticipate when I use it for my communication engineering problem? Right? You can ask the same question. Can't we have ANN with multiple layers? Right? We already have backpropagation neural network, which is one of the commonly used traditional artificial neural network. Just increase the number of layers and give the same name, backpropagation neural network. But why should we go for this complex architecture? The student has framed that architecture, right? But there is some specific idea or concept, or he found a drawback in the traditional multi-layer networks, right? What drawback he found? To explain that, I have taken a small application, right, for number recognition. That student, he used, say for example, a digit recognition application. So he will train the machine with all the characteristic features of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, say for example, and the machine should identify whenever a new data is given, whether this is 0 to 9 or not. So the general block diagram for the traditional artificial neural network is, everybody must be knowing, most of you must be knowing, you have the database and you have some pre-processing if necessary, we will do that. Then we have this important concept of feature extraction. What is the main purpose of feature extraction? To give in a single line, I can say that a raw data is converted into a number. Okay, why do I convert an image or a signal or whatever raw data into a number? Because I am going to have my machine learning algorithm in the computer, which can understand only number. I cannot just take the photo and paste it on the screen of the computer. That is not possible. The language of human beings is different. The language of the computer is different. So this is a very important block without which we will not be able to do the process. So this is very important, which helps in converting my original data into number. Then I have my neural network. In the recognition block, I have my neural network, and then it gives me a result 0 to 9. But that student, he observed that most of the time, irrespective of training the model with as much database as possible, he couldn't get a very high amount of accuracy performance measures. He was always stuck in a specific area, say for example 60 to 70 percentage or 70 to 80 percentage, and he couldn't move forward. Now, he did not take another existing methodology and tried, but instead he sat down and he thought for a while and he analyzed, why am I not getting the sufficient amount of result in the methodology? And he found one culprit who is mainly responsible for the reduction of the performance measures, right? He or she is nothing but the feature extraction block. So far, 25 years back, all the research community in machine learning and AI were praising this feature extraction block. And they say this is wonderful so that we can do all sort of pattern recognition applications, right? But that student, that one person's idea, he says that I can still do the process. I can still do the process without the help of feature extraction. When I say without the help of feature extraction, what he suggests is, let us not have feature extraction as a separate block, but let me include feature extraction within the recognition block, right? So there will not be any manual extraction of features in deep learning or deep neural network approaches. A breakthrough invention, right? Normally, we do not look at why we go into deep learning. We just say, okay, here we have artificial neural networks. It gives 80%. Now I go and implement with deep neural networks and it gives 90%. Okay, my deep neural network is good and it is always appreciated. But the reason is one single block was removed. Now, what are the benefits of removing this manual feature extraction? When I say removal, it is not removal, or I can say that the process is automated by mixing it with the recognition process. But in neural network, it is treated as a separate block where the user or the human being should extract features or should convert the data into numbers and give it to the recognition block. Now here in deep neural network, this process is automatically done by the recognition or the classifier block itself. What are the benefits? How does the accuracy increase if we go for such type of methodology? For that, you must know what are the advantages of eliminating manual feature extraction. So far, we depend heavily on the user's expertise. Say, for example, I pick two random names from the group sitting on the other side. I have never seen them. And if someone asks me to distinguish between these two people, how can I do that? I will not be able to do. But till 2000, people were doing the same without knowing there is a problem hidden within that. However, when you give the responsibility of feature extraction or converting the raw data into number to the machine, the need for the expertise of the human being can be significantly avoided. When the expertise is not required, there is more freedom for the user, and because the machine knows what exactly I need to distinguish these two persons, the probability of getting better accuracy will automatically increase, because the mistakes which normally the human being will make in extracting the features will not be there in the automated approaches. He solved the problem of pattern recognition. From 2000 onwards, there is significant increase in the deep neural network methodologies, and people are now completely engulfed with this concept of deep neural networks, right? The performance increased, and there are plenty of medical applications, wireless applications, which are extremely beneficial for the industries and the human society. This is the way how a problem need to be solved. That's how, or that's why a deep neural concept or deep learning approach came into existence. Now I will just give an explanation for point number A and B with a case study. We will take the same digit recognition application, right? So this is the digit recognition data set. Now, say for example, I am not an expert in identifying 0 to 9. Just assume I do not know anything about this. So when I look at the data or the input, I think that okay, vertical lines can be a good feature for the machine to distinguish between all these digits. But what happens here? You have vertical line in 1, you have vertical line in 4, you have vertical line in 5, you can have vertical line in 7, you can have vertical line in 9. So when you have mixture of vertical lines in more than one digit, the machine will have a confusion. This is what is happening with artificial neural networks. So the accuracy or the performance measure significantly drop down. Let me take horizontal line. Now look at the figure. In a horizontal line, you can write 0 in such a way it has a horizontal line. You can have 2 with a horizontal line, 3 with a horizontal line, 4 with a horizontal line, 5, 7 also with horizontal lines. Again, it indicates horizontal lines is also not a good feature, which is not known to the human user. Small circles, you can write 0 in such a way it has a small circle. 2, 6, 8, 9, all these can have small circles, which will again cause confusion, right? So when this process of feature extraction or the conversion of raw data into numbers, responsibility is given to the classifier as such. The changes were done in the methodology in such a way that there is a specific portion within the classifier itself which will do the process of feature extraction before giving the data to the classifier. This is how our deep learning process or deep neural networks came into existence, and neural networks were completely replaced. Even now, if you are doing any applications with 5G or 6G and beyond, or any wireless communication applications, I would suggest you use deep learning methodologies. Okay. Now we will go to I am not going to go deep into the types. We will go into one subset of deep learning methodology, okay, which is called as deep feed-forward neural network. Right? The diagram which I displayed to you earlier is an example for deep feed-forward neural network, where you will have more number of layers. Now you have a very good mindset that deep feed-forward neural network is going to give better result than traditional artificial neural network. So you simply have a mindset that when I increase the number of layers, my performance is going to improve. Happy? Very good. Definitely you will get good results. But again, there is another problem which was encountered in deep feed forward neural network. What is that? We will take the same case study of number recognition, right? 5 minutes back, I told deep learning is very good. Now I am saying that it is not that good, okay? Because of the problem, specifically the deep feed forward neural network, right? When I gave this data to my machine, right? Number 8 and number 5 to the machine. And when I trained the machine with this type of data, it was very good. It gave me very good results. And during the testing process also, it was very good. And it gives me an answer that the input data is 8, right? And when I give another number, it says it is not an 8. Perfect. Now, look at the second data set. When I give this data, when the scientist gave this data, right, same 8, same 5, and they try to train the machine, and they want to have the machine give the correct answer when it is given as 8 in a testing data as 8, and when a 5 is given, it should say it is not an 8. Okay, but what happened? The machine got confused. Right? Now, the inventor of this deep feed-forward neural network also should be very much disappointed. Why? The same 8, now it is not giving me correct result. What is the problem? Is it problem with the time? Is it any temporal problem with the machine? Or is there any other background setting which is affecting? No, everything remains the same. But the only difference here you will find is, can anyone tell me, is there any difference between these two data sets? Anyone would like to give a try? No? Okay, no problem.
Participants, you can unmute and tell
Yeah,
your answer.
you can unmute and give your answer also, nothing wrong. Okay, so here what happens is, you have this second set of data, the position of the data. See how minute details in our engineering applications are creating big problems. When the number 8 is present in the center of the image or center of my complete data, my machine is able to identify and give me a perfect answer. But when my number is not present in the center, what happens? It struggles. Right? This is another big problem. When they thought that they solved the problem of pattern recognition, another problem came into existence. So how can we solve the problem of having this type of data for pattern recognition? Right? You cannot expect always your data should be in the center. Right? When you take a selfie, do you think that always you will be in the middle of the picture? That is not possible. Okay, that is not possible. So when you have such data, how can I solve the problem? So another scientist came up, another researcher came up, and he gave an idea. Okay, let me have a very big large data set by having 8 in all possible positions. And again, the size of the 8 also will play a crucial role. I have given some samples here, right? So they have given in corner, the lower side, the upper side, on the middle side with the smaller size and everything. Now my question is, how many positions are there, practically speaking, and how many different sizes are there? The answer is infinite. Then how a human being, how a user, or how a programmer can write or develop data set with all positions and sizes. Already your machine is going to suffer with huge computational complexity because you already increased the number of layers because it solved the previous problem. Now we have another problem, right? So what can I do? Again, another researcher came up with the concept of supercomputers where the computational time can be significantly reduced irrespective of having a huge data set. But whenever you go for a huge data set, even though you use the best possible system with high spec, still there will be always a drawback in terms of the time requirement. So this will not be a clear cut idea or solution. It can be a solution for a maybe one or two simple problems. When the problem increases, when your application quality increases, it is always going to be a big headache, right? So how can we solve the problem? And here comes another idea by another student, right? He framed the idea of bringing convolution, which we normally study in signal processing, into the deep feed forward neural network, right? He says that let me take the concept of convolution and put it into the neural network, and this convolution will take care of the position invariant problem of my data, so that let me give my data irrespective of whether my region of interest is in the center, middle, top, or on the lower corner. My machine learning model or my deep learning model is going to give you the best answer or best solution. Right? This was his problem solving capability, and when he introduced this concept of convolution in the traditional feed forward neural network, there was again a boom in the deep learning um, arena. And here comes our convolutional neural network. C stands for normal traditional signal processing convolution, and then the NN stands for the deep feed forward neural network. When you combine these two things, you can solve the problem of feature extraction, you can solve the problem of position invariance, and also you can solve the problem of low performance measures. This I have taken from Wikipedia. You must be knowing convolution is a mathematical operation on two functions that indicates I need to have two input, right? To produce a third function, which is my output. But when I look at my output, which I'm going to call it as a modified version of my original input, one of my original input, right? Then I can say that my modified version is going to give me the position. Can somebody mute your mic? I think some mic is.
Sir, done, done.
Yeah, okay. It's okay. I understand. So the other way, the modified version will give you the different position, sizes and shapes of the input data. How he thought, right? It's very interesting. Most of the time we never think anything of that sort. We have an operation, we have a function, we have a methodology, we just take that and use that. But he did use the same convolution operation and used in a different way. Let us see how this convolution is used to solve the problem of feature extraction, position invariant, and also improving the performance measures. Right? Let us take a simple data, right? Because it is object recognitions or data recognition, I'm using an image. Now you can see a small child sitting in the middle of the garden, right? A human being can easily recognize the child, no problem, right? Now you assume that this child is not in the middle, depending on the position and the size of the other object. Now the duty or the responsibility of the machine is to identify the same object with the help of this methodology of convolution. Let us see how convolution is going to solve this problem. So when you use convolution, you are going to take this data as the original image or input number one. And he used another random data, right, or empty data, or an image without any information, which is just a matrix. You might be knowing that image is usually a matrix. He took that matrix and he named it as image number 2 or data number 2. So now you have function f and you have function g. He convolved both this data, both these images, and he created different overlapping small images, which we call it as tiles, using a methodology called as sliding window technique. This is how the process will look like. The output of the process will look like. The original image is there. Now, when you take this image and another empty matrix, when you go for convolution operation, right, you have the shifting operations, and now you will find that the complete data is broken down into small pieces. How the size of the pieces is decided, it is based on your data number 2, the small matrix which you have taken. When the size of that matrix increases, the size of the broken piece also will increase. So this is what the convolution is doing with an image. But that is not our region of interest. But what is our region of interest? Now come to the first row of the small pieces of the image. You can see that in the 1, 2, 3, 4, 5, in the sixth tile, you can see the head of the child on one corner, on the right corner, bottom portion. Look at the seventh slide, the next tile. You can see the head of the child in the middle bottom portion. On the eighth slide, eighth tile, you can find the head portion on the left side. In the same way, when you come to the second row, third row, you will find plenty of the body parts of the child, plenty of the features of the child, which helps you to identify that there is a child in the garden available in different positions and different sizes in different tiles. Again, there is a problem here. I do not see the body part of the child in all the tiles, right? There is another problem with this methodology. But again, instead of having the child in a single tile, having the child in more than maybe 3, 6, 9, 12, 15, close to 20 or 22 tiles, the probability of having a better performance measure, the probability of converting the data into a real number accurately, the probability of solving the position variant problem will significantly increase. That is how convolution neural network completely removed the concept of deep feed-forward neural network. There was a small patch of years, maybe 3 to 5 years, where people were using only deep feed-forward neural networks. But somebody faced this problem. There is always scope for improvement. And then the solution for that problem came in the form of convolution. It is a 3-step process, our convolutional neural network. I'm not going to talk about CNN because then I will go completely into the machine learning or the deep learning process. But my ideology is to give you more problems in the methodologies or in the technologies available and trigger your thoughts to find a solution for that, right? You have an input image, you have different convolution operations, and in CNN, normally this operation is not done in a single phase or a time, but done multiple times. Then we had a concept of max pooling. What is this max pooling all about, right? As I told you, you look at this image, only in 20 or 22 slides, you will find that the body part of the child is available, which helps the machine identify the object. But other tiles are waste. They are just sitting there and eating your computational capability or computational complexity. How can you reduce that? Then he framed the concept of max pooling, and these two processes, convolution and max pooling, became a predominant option for pattern recognition until 2025. Now we talk about quantum computing and quantum machine learning, but that is only for increasing the speed. But still, the YOLO models, different types of CNN models, take any deep neural network, you will always find a tinge of CNN always inbuilt within that, because this solved the problem several times. You see the three process: convolution, max pooling, and neural network, and the performance measures significantly increased. So we had ANN. From ANN, we saw about deep feed forward neural network, and from deep feed forward neural network, we saw about CNN, where the accuracy is extremely very high. Right? So this is a small explanation on how the convolution process will be able to identify the information to go. Maybe I will take 2 to 3 minutes on this. You see a picture of a dog here, right? But the computers will not see the picture of a dog. It will see only numbers, because an image, at the background we have the pixel or the picture element, where each is going to have a gray level value. If it is a color image, you will have multiple values. Now what convolution is going to do is, it takes this original image and it will take a small matrix, say for example of the size 3 cross 3, 3 cross 3, with values ones and zeros of different direction, maybe in the diagonal or maybe in a plus shape or whatever. It depends completely on the user. We call that as a filter, right? We call that as a filter. Now what we are doing in the convolution is, we take this input data or image and we convolve it with, or we say overlap or multiply with the filter data. Now the filter data size is very, very small. So it is going to fit into one small portion of this picture. So that portion of, say for example, if it is 3 cross 3, that 3 cross 3 portion of the picture at one corner will be coming out. To explain this situation, you can just assume you are taking a torchlight, okay, in a dark room. You are entering a dark room, and maybe someone has asked you to find an object in that dark room, maybe a mobile phone. Right? What you will do? You will take the support of the torchlight or the flashlight. The torchlight or the flashlight here is the filter, and the dark room is the original image in which you are going to search for the dog, or in real time situation we are going to search for the mobile phone. So now what you will do after entering the dark room, you will switch on the flashlight and you will focus towards one specific portion of the room randomly. Okay, your flashlight is not very big, it will not cover the entire room. It is going to give you one focus only. That specific portion of the image or room will be given to you. That is called as the small child, which I displayed to you in the previous figure. Now the question is, which one is important, the dark room or the flashlight? Both are important, but the flashlight is more important. When you are looking for a mobile phone, the size of the matrix or the filter or the numbers, it doesn't matter, because the object is relatively big. But when you are looking for a needle, you cannot have again a normal filter. What you should do? The matrix values or the size should be changed in such a way you can find the needle. So each time when you focus on a specific portion, each time you will be given different regions of information, right? You are going to scan completely the room, and in an image you will move from your left side to right side in a column wise, in a row wise fashion, then in a column wise fashion, and you completely take the information. Each time when you come or go through this specific object, you will get small information. At one point of time, you will find the ears of the dog. The machine will find the ears of the dog. At another point of time, it will find the eyes of the dog. Then it will find the tongue of the dog. So the problem can be solved with the help of that matrix or filter. Technically speaking, we call it as kernel in learning language. But the size of the kernel or the filter should be always lesser than your original data. When you do convolution process, when you just multiply the values of your small filter size, maybe a 3x3 matrix with the specific values in the original image, right? You can get, and you can sum up, that is convolution. You sum up and you will get a single number. Now you move to the next position. Again, you multiply, sum up, you get a single number. Go to the next position. Likewise, you completely move through that, you will get many single numbers. When all these single numbers, which are in a single value, is converted into a matrix. A matrix is nothing but an image. You will get the small portion of the image which I showed you. So in this example, I got 784 locations, torchlight locations, 784 single numbers, and then I received or I converted them into a 28 cross 28 size matrix, which is very much lesser than my original image. So convolution does this process of converting the entire image into small pieces of tiles. This is the mathematical scenario of that specific process. You can just have the red color shows the filter or the kernel, the blue color shows the original matrix, and you just move on. But maybe a sliding window or without any overlapping also you can do. The choice is with the user. And finally, you will get 9 numbers, the green color. And when you arrange the 9 numbers in the form of column and rows, you will get a 3x3 matrix, which is a sub image of the original big image. Likewise, you will get many green color small pieces. This is an example on my right hand side where you will see the gray color rectangular boxes, right? Each box is a tile which is going to give you some information about the object. Now my question is, if I do not show you the picture of the car, right? If I show you only that specific 6, 9, 10 rectangular boxes, will you be able to identify the object? It is not possible. It is not very clear. So what we are going to do is we are going to repeat the process again and again. Right? One example I have given here is the size of the filter I have shown here, but I am not showing you the original image. Can anybody guess what could be this original image which I am talking about? I will repeat once again. I am showing you the filter. I have taken a 7x7 filter. Okay. I have convolved this with the original image where there is an object. An object is hidden. When I did one step of convolution, as I showed you earlier, I got this region. Or you assume that you are showing the torchlight or flashlight on a specific area in the room. You got this portion of the image. Can anybody guess what object am I talking about? Any answer? No? Okay. You may think this is an elephant. Okay. This may be a giraffe, but this is actually a mouse. The back portion of the mouse. So it clearly indicates, even though CNN is extremely good, that researcher found out the problem with one step of convolution, which is not sufficient for object recognition. So what normally we do is we repeat the process with more convolution steps so that the different regions of the image or the data will be given with more clarity. Right? Say for example, When you look at a table or a shelf, okay, you will have four small edges. Low level features in the sense are the first level of convolution will give you only lines. There will not be any connectivity. But when you go for the next level, you will get an L-shaped object. So when you have an L-shaped object, you can narrow down on the number of possible objects you can find in that specific data. That is the beauty of artificial intelligence or machine learning. Our brain works in the same way, and also our convolution layer processing also is working in the same way. So when you go for third, fourth, fifth and higher lines, you will find that all the complex features can be identified, which can give you a better identification of the specific object. And people were very happy with CNN, and you will find everywhere the CNN coming or playing in the application. Now again, as I told you, there is a problem with CNN because all the tiles are not going to be beneficial for the application or for the recognition. So what can I do? I should remove some of the tiles or the unwanted objects. For that, again, he introduced another concept called as max pooling, where I am going to take a specific set of, or I can say a subset of matrix from the whole set, right? I'm showing you two pictures. In the first picture, you can see the multiplication and summation value 6,600, right? The multiplied and summed up value. But on the second picture, right, I have showed the torchlight on a different area. I find the multiplication and summation as 0. Why? In the second picture, in this picture, I have shown the torchlight on a wrong direction, so that there is no useful information for the machine to identify that there is an object. So here comes the hint. How can we solve this problem? Just do the convolution, and whichever tile, whichever subset of the image is giving a larger number, retain that. Whichever is giving a lower value, you can remove that. Because you are going to retain that, we call this as max pooling method or max pooling layer. Nowadays, we have several variations. We are not going to go into that, but I'm just saying that we can solve the problem of removing the tiles using this max pooling method. Right? And next comes our normal artificial neural network, or I would say deep feed forward neural network. This is the way how the process of pattern recognition changed from 1990 to 2020. Plenty of benefits in all types of applications. I am also showing you the training process. Once the structure is decided for a machine learning process, we are going to do the training, right? Mathematics is very important, but I am not going to talk about mathematics now, right? Only when you go deep into the concept of a specific model or methodology, you will find out the drawbacks within that. Otherwise, the drawbacks will not be shown to your eyes, and there will be no innovation or creation from you on your specific research work. These are some mathematical operations which are very complex. We use the chain rule, and when the number of layers increases in the final deep feed forward neural network, it becomes more complex, right? Now, after looking at these mathematical equations, what conclusion will you come to, right? If you are not good in mathematics, you may think that, why should I go for CNN? Let me stop with ANN only, or deep feed forward neural network only. So it indirectly indicates, irrespective of having high accuracy, the convolutional neural network still suffers from the problem. Note down this sentence, still suffers from the problem of computational complexity. On one hand, we boast about accuracy, but it takes huge amount of time to get the results. Why? Because of the complex training process, the chain rule of differentiation, and the number of layers stop it from giving the results at a quicker time. Right now, there is another problem popping up. We came from ANN, we are not satisfied with ANN, we went to DFNN, we are not satisfied with DFNN, we went to CNN. Now, after working with CNN, again we find that there is also a problem with CNN, and I want to solve the problem of CNN. What is the problem of CNN? It is the computational complexity. Why computational complexity? Why do we have these many complex mathematical equations? Because the architecture of CNN is arranged in such a way that your convolution and max pooling layer put together, the red color box which I'm showing here, does the process of feature extraction, where the next recognition or classification is done by the blue color box. I need parameters to be identified in the feature extraction block. What are those parameters? The size of the filter. As I told you, finding a needle and finding a mobile phone is not the same. So when the size of the filter or the kernel or the matrix changes, I need to find the exact correct values. Not only the size, the values also play a major role. So that needs training, adjustment, continuous adjustment. Now that is on one side, the red color box. Come to the blue color side. You have your traditional DFNN. Again, you have many layers. As you might be knowing, each layer is connected by weights. Again, you need to find the weights also. Now the problems become twofold. In ANN, you have only the blue color box. Now, in the guise of automating the process to improve the accuracy, you included a feature extraction red color box, which is again affecting you in terms of computational complexity. All right. So now what is my next headache? How should I reduce the computational complexity of CNN? And there comes the next transformation in the deep learning process, which is called as transfer learning. Transfer learning is another interesting concept which solves the problem of complexity in CNN. As an editor, whenever I enter into my login to check the papers for the review process, most of the time the people would have used transfer learning and justifying saying that it has improved the accuracy. Yes, of course, it does, because we will remove the irrelevant concepts, or the features are already trained. That is fine. But the main focus is not that. The main idea of having transfer learning is not that. In transfer learning, what we do, before going into that, let us have a small idea on transfer learning. What is this concept of transfer? Human beings always have the capability of transferring knowledge from one task to another task and one domain to another domain, right? When I say driving, I can ride a bicycle or I can drive a car, right? This is a task. The domain will vary. I can act as a pilot or I can act as a captain guiding the ship. So the vehicles differ, right? But the task remains the same. But transfer learning says very, very interesting concept. It solves the problem. It says that once you know the art of riding bicycle, right, it will be easy for you to learn another vehicle. There will be some conditions depending upon whether it is motorized or non-motorized. But human beings have the capability. If I know to write an English language paragraph, I can also write a Tamil poem or Malayalam poem or a Hindi essay. The writing, the task remains the same, the domain will change. Based on this basic human behavior, right, we have four different sub-classifications: same task, same domain, same task, different domain, different task, same domain, and different task, different domain. Same task, same domain, it is very easy. Different task, different domain, we are not going to bother about that. But the category B and C, this is the place where we are going to importance or relevant for our transfer learning in the concept of CNN. Right? This is a small example I am giving you. So because of the want of time, I'm just skipping this information. Now, in deep learning, specifically in CNN, right, we say that there are two set of weight matrices or two set of parameters which needs to be solved or which needs to be identified. Now, when I say that it is computationally complex, another person's thought process came into existence and he says, okay, once I do a process, right? Say, for example, I do a brain image classification. Now, from brain image, if I go to a lung image, which looks exactly similar to that of the brain, the condition applied, exactly similar to that of the brain, should I again go and change those two parameters? Instead, can I freeze or can I fix the initial blue color box in CNN and I adjust only the red color dashed box, which is nothing but the DFN weight matrix, so that I can get the same accuracy, right? There will not be any compromise in the accuracy. I will get the same accuracy, but I will have it at a quicker time. They tested it, they experimented it, and they found that that is always possible, right? But there is one condition: the data or the type of the domain which you are using should be similar. If they are similar, you need not repeat the task again and again and again, right? You can have the same architecture, you can have the same filter parameters which has been already trained, and then you can adjust only the last layer DFNN weight matrices. This is the idea of transfer learning, and with this idea, I will skip all these things. With this idea, we have got plenty of different modifications of models, or we call it as pre-trained models, which are nothing but actually transfer learning models, right? VGG16, VGG19, inception, V3, exception. These will have different layers depending on their numbers, but the concept remains the same. These networks are already trained. They are already trained with lung images, lion images, peacock images, house images, car images, lorry images, big truck images, cycle images, cellular images, molecular images, you name it. So they say that if you have an input data to be tested, you need not go from blue box to red box and then go to the output. You can give the input, but straight away you can take the values and go to the red box. This is how the computational complexity aspect of CNN is attacked in your transfer learning approach. So some people think that transfer learning is something new. Transfer learning is not new. It is just a variation or modification of our traditional convolutional neural network with the sole objective of making or reducing the computational burden of CNN. Now the condition is, or now the problem again here is, sir, I have a data, right, which is completely different from the images or the data which are used to test this VGG 16, 19, inception, V3, exception, resonant, so on. What will happen? Your system will fail. Your system will fail. You will face a problem. Unknowingly, our research scholars and sometimes academicians too, right? They randomly pick some models, any models, and they use their data and say that they are getting good results without actually checking whether that similar type of data, need not be that exact data, whether that similar type of data is already tested for that specific model. Do a small homework, do a small check whether such data is already used then you can go for the training process without adjusting the weights of the first layer or the blue color layer. Right? So there were plenty of models. I will skip all these things. All are very useful, right? And it was very commonly observed that transfer learning. Nowadays, you see research articles, everybody, I think most of the people sitting on the other side, if I ask, they will raise their hand. They have used these models for their application, any sort of application, right? So ANN, then we had the DFNN, then we had CNN. From CNN, we went to pre-trained models or your transfer learning models. 4 stages are there, right? Now, people are saying that pre-trained model is also not good enough, right? All the methodologies which the human beings have invented will always have some problem. Don't think your models will always beat the human brain. The human brain was created by God, right? Models are created by the brain which was created by God, right? Then there is no way, when it comes to the second set of creation, there is no way it can beat the brain. But we think, but we say, but we try to make sure that it matches with the capability of the brain. Now the challenge I am giving to you is, how can I make still change in this process so that I can use in a better way for my application? Right? I completely eliminated the blue color feature extraction training process. That is fine, but still the red color box, the DFNN, is always complex. It is going to have more time, or it is going to take more time for my training process of my application. What can I do? Right? So we did, this is not anyone's innovation. This is my own innovation. We developed an output, right, to make sure that we can attack the computational complexity of fully connected neural network. This is how the research work, the problem solving process, or the problem statement selection process, or the application process should come up, right? Feature extraction block, we leave it as the same as that of the pre-trained model, but we take this DFNN, the green color inputs, the red color inputs separately, we take it out, right? We do some process. Then after doing that process, which is relatively simpler than the training process of the convolutional neural network, then we go and fix in that specific place. Maybe I will take another 5 minutes, right? Then we can go to the question answer session. And I am explaining you with the help of application where we have taken for pattern recognition or object detection in a brain image, where we have used the traditional BPN, which is the fully connected layer, or the DFNN available in the last portion of the CNN, right? Now you need to have some visual understanding of zooming in of that green color and the blue color dot. Just you have that in your mind. You have the conventional BPN. Now we went for the modification, especially in the training process, with an objective to reduce the complexity, not to increase the accuracy, because I know it is already accurate. What is the meaning in again going and making some changes to improve the accuracy? But at the same time, I will ensure that my accuracy will not drop down. So this is what our traditional architecture will look like. Okay, you have 8 input layers. The first the first column is the green color, which we saw in the CNN. The last column is nothing but the red color, which we saw in the CNN. In between that, you have multiple layers. This is the traditional BPN, which is normally a 3-layer network. If you try to increase the number of layers in BPN, then again you will face the local minima problem. Okay, that's why we will not increase the number of layers in BPN. We do not use the same stochastic gradient algorithm. We go into a different sort of algorithm for deep neural networks. So here you have the conventional BPN, and these are the equations. I will not go in deep into that because explaining this will take more amount of time. These are some mathematical steps. This is available in the textbook or in the literature. You can go and find. Okay, you have a weight value, you have an input value, multiplied together, you will say you find a net value. From the net value, you will find an output value. How many outputs you will get? Two outputs, because you have two layers. The first output is not exactly the output, but we can call it as an output of the hidden layer, and then it comes to the final output. For the time being, you keep in your mind that y is the final output. Then we go back propagation, very effective process. I read in one of the literature that in 2025 also the same concept of back propagation still exists. A Nobel laureate has given an excellent writing on that. Why it did not change? What are the benefits? Right? You can go deep into the back propagation. We are going to adjust the weights coming in the backward direction. You will find that you will have new set of weights V, J, K, and U. For the time being, you just understand that in the architecture you have U and V, and we have found new values of U and V. This process will be keep on repeated for several times, for several iterations, and finally you will get the U and V, right? That is fine. But look at the expressions, step number 6 and 7, that looks simple. F dash, when it comes to F dash, it is a chain rule where you need to differentiate a variable within a variable. When it comes to del J in step number 7, del K comes within that. That will make the operation exponentially high. If for two layers like this, if you add even one more layer, the number of mathematical calculations which you have to do in traditional stochastic gradient algorithm will increase. Right? Accuracy wise, no problem. They are good, but the only problem they face is it takes around 1650 CPU seconds. Now, what we did in this architecture, right? We take the DFNN alone, and we did a change in the architecture and in the training algorithm. What we did, we gave the target values, because it is a supervised network, both to the output layer and also to the hidden layer. You can consider the architecture as same. There is no change in that. But the only change I did was giving to both the layers. That is a reason why I gave to both the layers. I am going to do the weight adjustment in the reverse direction, right? What happened in the traditional BPN? First, we came from the front end, went to the back end, then we went in the reverse direction. But here I am not going to do two times. Straight away, I'm going to start from the back end and then come to the front and adjust the weights. But for that, I am making a small compromise, I would say, in the error value. I am fixing my error value as 0.01 with an objective that error value can never be equal to 0. But if any of you can prove and if you can validate the error value can be 0, then this process or methodology will not be valid. Here I say practically it is 0.01, or you can fix it to 0.001 also. So if you know this algorithm, when you come from the backward side, you will have this net value because you know already the target value. With the help of this net value, you take the reverse, exponential will become logarithm, natural logarithm. You will find the values. With the help of the matrix, you can find the value u. The same thing, because I have given the target to both the hidden and the output layer, I can do the same process two times, one for the hidden layer and the output layer. Same process, I am fixing the same target, but the values will change. Okay, I have also the net value of set j so that I can find the v value. Now I have the u value and the new v values with me without having any differentiation operations. There is no chain rule of differentiation. So what happens? My accuracy, no significant or dramatic change. I am not claiming my accuracy has improved, but look at my time period. Because I have removed the differentiation operation and doing the calculation in a single stretch, my time requirement is less than 1 CPU seconds. When I take this architecture and this weight estimation formula and fix it to CNN, I can deal with any complex applications irrespective of the number of data. ANN, DFNN, CNN, pre-trained models, and next you need to develop, this is a small case study, you need to develop some methodology on your own so that you can always have good solutions for your problems, right? Please keep in your mind the rejection of your article is not based on any other problem, but it is because of your weaker problem statement. When you make the problem statement challenging, when you go deep into the technology and then develop machine learning or AI algorithms, doesn't matter. It is an antenna design application. Doesn't matter. It is a radiation pattern estimation application. You can use it for any type of application provided you have logically, mathematically, and experimentally correct methodologies. Right? Thank you for your patience listening. Due to want of time, I will stop here. This is my email ID. This is my WhatsApp number, and you can get connected with me in LinkedIn. I will post all the special issue calls or any recent informations recruitment in the LinkedIn post. You can follow that and you can get information, or you can contact me in WhatsApp or mail also. I will try to help you as much as I can. Now we will go to the question answer session, ma'am. We have another 10 minutes time.
Dear participants, if you have any query related to AI, artificial intelligence algorithms, you can clarify with sir.
You can unmute your mic and ask, or you can post it in the chat box. The organizers can read and give the questions. People are asking for PPT. Kindly share the PPT, right? That is one easy way of getting the information, right? But
Share the recorded video.
okay, that's fine. Recorded video is much more better. That's what I'm trying to say. PPTs, if you look at the expressions, variables, you may not be able to understand. But when there is some explanation, it will be always good for you. Any questions? Okay. Ma'am, are there any questions, ma'am?
No, sir. Till now, no questions.
Okay.
Share.
We will wait for 1 or 2 minutes, or we can wind up, give them a break for 5 to 10 minutes before the next session starts. Maybe you can wind up, ma'am?
Yes, sir.
Okay.
So thank you, sir. Thank you very much for spending your valuable time with us.
Okay.
Thank you, sir.
Thank you, participants. Thank you very much for your patience listening in this evening time. Be in touch with the organizers. If at all you need some help or support at any point of time, our organizers will be always happy to do that. Thank you very much.
Thank you, sir.